So today we are going to start with the experimental skills. So total there are 18 experiments and most of them are very simple, and we have already covered most of them. Okay, so this would be much of the recap, right? So now let us see the first experiment, measuring of the length of small devices, you can say small objects, okay, using the Vernier caliper. Okay, so for an example, suppose you want to measure the thickness of this pen. Okay, so for that you will make use of a device called as Vernier caliper. Okay, so how do you use that? So suppose you want to measure the thickness of this pen. So there are these two jaws. Okay, so you will put this pen in the two jaws. Okay, and then you will take the reading. Okay, so let's see how do you take the reading. So there are two scales. One is the main scale and one is called as the Vernier scale. So there are two scales in the Vernier caliper. One is the main scale, the other one is called as Vernier scale. Okay, so here it's shown in simplified form. So this is the main scale and this one is the Vernier scale. Okay, you can see this is the main scale. So n number of divisions on main scale will match with some number of divisions on the Vernier scale. Okay, so here you can see 10 divisions on the Vernier scale match with 9 divisions on the main scale, right? 10 divisions on the Vernier scale, okay, they match with 9 divisions on the main scale, right? So using this information we can find out the least count. Least count meaning the minimum reading that can be taken using this device, the minimum length that can be measured using this device. Okay, it's known as the least count of the device. So here 9 divisions on the Vernier scale, 10 divisions on the Vernier scale match with the 9 divisions on the main scale, right? So this is one example. There can be several scales. For an example, 10 divisions can match with 8 divisions. Okay, 10 divisions of Vernier scale can match with 8 divisions on the main scale, right? So in general, not in general, this is a specific case, but most probably it will be this case, right? So let's see how do we find the least count of the Vernier caliper. Least count is defined as one main scale division, MSD is main scale division, minus one Vernier scale division. Okay, one main scale division minus one Vernier scale division, right? So now if n divisions of Vernier scale match with n minus 1 division of main scale, so for this particular example we are going to find out the least count. Okay, so then that means one division of the Vernier scale will match with what? Take that n on other side, right? Because see, the distance equal to n divisions of Vernier scale is equal to distance equal to n minus 1 division of main scale, right? So then you can move n on that side, so you get distance equal to 1 division of the Vernier scale. So that would be equal to n minus 1 divided by n divisions of the main scale. Okay, so then why is this least count this much? 1 main scale division minus 1 Vernier scale division. So for that we can understand it this way. So this is a main scale division, this is one main scale division. Okay, if you see it on the scale, so this is one main scale division and this one is one Vernier scale division, right? So what minimum distance can we measure here? It's this much. What minimum distance can we measure here? It's this much. Okay, so using these two scale, what minimum distance can we measure? So this is a main scale division and this much is the Vernier scale division, right? So using these two scale we can measure minimum distance equal to this much. Okay, because there is one marking here, one marking here, right? One main scale marking is there. Okay, this is one main scale marking and this is one Vernier scale marking. So these two markings on main scale and Vernier scale, they match. Okay, but here there is some gap, so we can measure this gap. How much is this gap? So it is this main scale division, okay, this main scale division minus the Vernier scale division, and that is the minimum distance that we can measure. So therefore the least count is one main scale division minus one Vernier scale division. So this thing is clear. Okay, good. So then we just found that one division on the vernier scale, that is 1 VSD, vernier scale division, is equal to n minus 1 divided by n divisions of the main scale, right? So therefore, what would be least count? So it is 1 main scale division minus 1 vernier scale division, which is equal to n minus 1 divided by n main scale division. And if we subtract this, what do we get? For this particular case, we get least count is 1 divided by n main scale division. Okay, the least count is equal to what? 1 divided by n of the main scale division. Okay, so suppose the main scale division is equal to x, right? So in this example, how much is x? So this is a centimeter scale. Okay, so 1 centimeter is equal to what? 10 millimeters. So this 1 division is equal to 1 millimeter, right? 1 millimeter, 2 millimeters, 3 millimeters, so on and so forth. So just for an example, suppose x is equal to 1 mm, and we have seen that what is n? The number of the vernier scale division that matches with n minus 1 main scale division. So that's equal to 10, right? And therefore the least count would be equal to what? X, which is 1 mm divided by 10, and that's equal to what? 0.1 mm. Okay, so least count is length of one division of the main scale divided by number of divisions on the vernier scale, right? Length of one division on the main scale, for an example, it's equal to 1 mm. So put that, and number of divisions on the vernier scale is equal to 10. So if you put that here, then you get 1 by n equals to 1 by 10 of one main scale division is 1 mm. Okay, so that is 0.1 mm. So this is how we find out the least count. Okay, so this is a specific example, but most of the times this would be the example. Okay, this would be the scale. Then now let's see how do we take the reading. Okay, so what is the reading of the vernier scale shown in this diagram? So this one is the main scale and this one is the vernier scale. Okay, so suppose you hold some object in the jaws, and then the vernier scale will shift. Okay, so now you will see this reading. Okay, where is the 0 of the vernier scale? So it comes after, see, this is 40 and it is in millimeter. Okay, it's in millimeter. So 40 millimeter of the main scale. So this is 41, this is 42, this is 43, this is 44. Okay, so therefore now what is the main scale reading? It is 44 mm, and the 0 of vernier scale comes after that 44 mm, right? Okay, and suppose for this specific scale, the specific vernier scale, it's the same, least count is same what we calculated. Okay, 9 divisions of main scale match with the 10 divisions of vernier scale. So least count would be what? It would be equal to 0.1 mm. Okay, so now how do we find the reading? So reading is main scale reading plus the vernier scale reading multiplied by least count. Okay, so suppose there is no error in this device, then the reading would be main scale reading plus the vernier scale reading multiplied by its least count. Okay, so main scale reading we have seen it's equal to what? 40 plus 1, 2, 3, 4, that means 44 mm. Okay, then what's the vernier scale reading? So here you should see which line of this vernier scale matches with some of the line on the main scale. Okay, so it is, which line is that? Is it? So it's 1, 2, 3, 4, 5, 6, right? Which division we should say? 1, 2, 3, 4, 5, 6. So sixth division matches with this line on the main scale, right? It can match with anyone. Okay, so the vernier scale reading would be 6 divisions. Okay, so 6 division multiplied by least count. What is least count? It's 0.1 mm. So main scale reading is 44 mm. Vernier scale reading is what? Vernier scale reading, vernier scale divisions multiplied by the least count. Okay, so that is 6 multiplied by 0.1 mm. Okay, so what's the total reading? So it is, this is 0.6, 44 plus 0.6 means 44.6 mm. right? This is clear? Tell me. Yes, no? Okay, good. Then let's see another example. What is the reading of Vernier scale shown in this figure? Okay. So main scale reading. So this is 3 centimeter, this is 4 centimeter. Okay, and you have the same scale, suppose. So this is suppose 3.1 centimeters, this is 3.2, 3.3, 3.4, 3.5, and 0 of Vernier scale comes after that. So what is the main scale reading? The main scale reading is 3.5 centimeters, that is 35 mm. Okay, and Vernier scale reading. So to check Vernier scale reading, you need to see which of the line matches here with some of the line with of the main scale. Okay, which line of the Vernier scale matches with some of the line of the main scale. So you can see here 9th line, okay, actually 9th division matches with some of the line, right? So what is the Vernier scale reading? It is 9, okay, and the least count is 0.1, okay. Vernier scale reading is 9. So then reading is main scale reading multiplied by MSD, okay. MSD means main scale division, 1 main scale division. So that comes out to be equal to 35 mm. And Vernier scale reading multiplied by the least count. What is the least count? It's 0.1 mm. So 9 times, so 0.1. So the reading is equal to what? 35.9 mm. This is the reading, right? So this thing is simple. Yes, no. So sometimes there can be an error in the instrument. So when there is nothing kept in the two jaws of this Vernier scale, then what should happen? 0 of the main scale should match with 0 of the Vernier scale. Okay, so in that case there is no error, no 0 error, right? If 0 of the Vernier scale matches with 0 of the main scale, then in that case, when Vernier scale is closed and both zeros match, in that case there is no 0 error. Okay, but sometimes those two zeros don't match. Okay, so for an example here, nothing is kept in between the two jaws of the Vernier scale, but still both zeros, they do not match, right? They don't match. So there is some 0 error, and if 0 of the Vernier scale, it falls ahead of that of the 0 of the main scale, it is showing some extra reading, right? So this is positive 0 error. Okay, so you are calculating something extra, right? So whatever is the reading, you need to subtract that from the final measurement. Okay, you need to subtract that from the measurement to get the final measurement, right? So see here, so in this case, this fourth line, 1 2 3 4, okay, it nearly matches, right? So this diagram is not that good, but fourth line matches with this line, we can say, and therefore what would be the 0 error? It would be 4 multiplied by least count, right? So that's 0.4 mm. Okay, so this is positive 0 error. This is positive 0 error. And then let's see another example here. 0 mark of the Vernier scale, it will lie before the 0 mark of main scale, then there would be negative 0 error. So here there is negative 0 error, right? So 0 error is -5. How is it -5? So you can see 1 2 3 4 5, fifth line of Vernier scale matches with some of the line of the main scale, but 0 falls before the 0 of the main scale. Okay, 0 of the Vernier falls before the 0 of the main scale, and therefore it's -5 multiplied by the least count. Least count is 0.1, right? So -5 multiplied by 0.1, so the 0 error is -0.5 millimeters, right? So this thing is clear. Tell me. Okay, good. So if 0 error is positive, you need to subtract that from your reading, and if 0 error is negative, then you need to add up that value to your reading to get the final reading. So let's see some questions based upon the vernier scale. So let's see this one. The main scale of vernier caliper has n divisions per centimeter. N divisions of the vernier scale coincide with n-1 divisions of the main scale. The least count of the vernier calipers is, tell me. If n divisions of the vernier scale coincide with n-1 divisions of the main scale, then in that case the least count would be equal to 1 by n, right? So this is the example that we have seen already. Okay, this is the example that we have seen already, that n divisions of vernier scale match with n-1 divisions of the main scale. So in this case we have found that the least count would be equal to 1 by n, right? 1 by n. Okay, is this one clear? Tell me. Right? Okay, good. Let's see next question. In a slide caliper, that's vernier caliper, m plus 1 number of vernier divisions is equal to m number of smallest main scale divisions. If d unit is the magnitude of smallest main scale division, then the magnitude of the vernier constant is. So in this case also, see the difference between number of divisions of the vernier scale, okay, that are matching with the number of divisions of the main scale. It's 1. Okay, then in this case also the least count would be equal to 1 divided by number of divisions on the vernier scale, which is equal to m plus 1 times of the least count, sorry, times of the MSD. Okay, what is MSD? If D is the unit, okay, if D unit is the magnitude of smallest main scale division, so see in this case also you have m plus 1 number of vernier divisions, they are matching with m number of the main scale divisions. So what's the difference? It's 1, right? The difference is 1. So whenever difference is 1, we will take 1 divided by number of divisions of the vernier that are matching with number of divisions of some number of divisions of the main scale. So it's m plus 1 and here it's m, right? So what is the number of vernier scale divisions? It's m plus 1. So it's m plus 1, okay, 1 divided by m plus 1 times of the main scale division. Okay, main scale division. What is the main scale division? The main scale division here is D. So that's why what would be the answer? 1 divided by m plus 1 multiplied by D. Okay, so this is the trick, right? So what's the answer? D divided by m plus 1 unit. Okay, this thing is clear, tell me. Yes, no? Okay, and now if you like, we can verify this using the formula. So how do we verify this? So you have m plus 1 VSD, vernier scale division, is equal to m main scale divisions, right? And therefore what is 1 vernier scale division? Okay, m plus 1 vernier scale divisions match with m main scale divisions, and therefore what is 1 vernier scale division? So it is m divided by m plus 1 main scale divisions, right? And then what's the formula for your least count? The least count is equal to 1 main scale division minus 1 vernier scale division, 1 MSD minus 1 VSD. So that's equal to 1 MSD minus m divided by m plus 1 MSD, because 1 VSD we calculated, it's equal to m divided by m plus 1 MSD. Okay, so you can take this MSD, main scale division, common, right? So this is equal to, this is just equal to, therefore the least count is equal to 1 minus m divided by m plus 1 times of MSD. But what was MSD? It is D, right? 1 main scale division is equal to D. Okay, So then just solve this. So multiply and divide this 1 by m plus 1. So you have m plus 1 divided by m plus 1 minus m. So that m plus m minus m gets cancelled out. So what do you get? 1 divided by m plus 1 times of d. Right? So that's the answer. Is this thing clear? Tell me. Okay. But you can remember this short trick. Whenever you have the difference between the number of Vernier scale divisions matching with some number of the main scale divisions, okay, if difference between them is equal to 1, then you will take 1 divided by number of Vernier scale divisions and you will multiply that with what? Main scale division, and you will get the least count, right? See the next one. The length of a strip measured with a meter rod is 10 centimeters. Its width measured with Vernier calipers is 1 centimeter. The least count of the meter rod is 0.1 centimeter and that of Vernier calipers is 0.01 centimeter. What will be error in area? Okay, what will be error in area? So if you remember our first chapter, so if you have area can be written as what? So here it's length times width, okay, it's length times width. Then what would be error in the area? You want percentage error. So you know delta A by A times of 100 is equal to what? Delta L by L times of 100 plus delta W by W times of 100. So L is the length and W is the width, right? So then length of meter rod is 10 centimeters. Okay, it is 10 centimeter. And its width, which is measured with Vernier caliper, is 1 centimeter. So you are given that L is equal to 10 centimeter and width is equal to 1 centimeter. Okay, but then the least count. So what could be the error in the measurement? It's equal to least count. Okay, so we write length as L equals to 10 centimeters. So 10.0 plus minus 0.1, right? Plus minus 0.1. Okay, so what could be the error? So error is this least count. Okay, so least count is 0.1. So you can say delta L is equal to 0.1 centimeters. And what is the least count of Vernier scale? So delta W, it's equal to 0.01 centimeters. And then put these values here in this formula. So what do you get? You get delta L, which is 0.1 divided by L is 10, this thing times 100, plus delta W is 0.01 divided by 1 times 100. Okay, so 0.1 times 100 means 10, right? 10 by 10 is 1. Okay, and this thing is again 1 by 1, that means it is 2%. So what's the answer? It is plus minus 2%, right? Diameter of a steel ball is measured using Vernier calipers, which has divisions of 0.1 centimeter on its main scale, and 10 divisions of its Vernier scale match 9 divisions on the main scale. Okay, 10 divisions on Vernier scale match with 9 divisions on the main scale. 3 such measurements for a ball are given as, so these are 3 measurements. If the zero error is minus 0.03 centimeter, so if zero error is negative, we need to add it, right? The mean corrected diameter is, so if you have 3 readings, okay, 3 values of diameter, right, and you just need to find out mean of that. Okay, so suppose this first reading is D1, this is D2, this is D3, right? So what would be D1? So D1 is equal to, it is main scale reading. Okay, how will you take reading? So any reading is main scale reading multiplied by main scale division, okay, plus you have Vernier scale reading multiplied by the least count, and plus you have zero error. right? Zero error. Okay, let's write what are the values of D1, D2, D3. So D1 is 0.1 centimeter. Actually, it's given directly. So it's 0.1 centimeter plus you have see 10 divisions of the Vernier scale match with 9 divisions on the main scale. Okay, so once again the least count is equal to what? 1 by 10, right? Because the difference between the number of divisions is what? It's 1. So then it's 1 divided by number of Vernier scale divisions multiplied by minimum reading of the main scale, right? Minimum reading of the main scale. Okay, so it's 0.1 centimeter on the main scale, right? So times 0.1, that means 0.01 centimeters. This much is the least count, right? So what is Vernier scale reading? First one is 8. So 8 times you have 0.01. Okay, how did I write 0.1 here? It's 0.5, no? I wrote 0.1. It's 0.5 centimeters. Directly the reading is given. Okay, so then what's the zero error? Minus 0.03. So add it up actually. So you have plus 0.03, right? Negative error is, if error is negative, that much value is added. Okay, so what do you get if you calculate this thing? If you calculate this, this is 0.1 times 8 times of 0.01, that means that is 0.08. 0.08 plus 0.03 is 0.11, right? So 0.5 plus 0.11 means it is 0.61. 0.61 centimeters. This is the first reading. Tell me what's the second reading? Again, the main scale reading is same, 0.5 centimeters plus you have the Vernier scale reading is 4, right? So 4 times of 0.01 plus 0.03. Okay, so this is 0.04 plus 0.03, then 0.07. So the answer is 0.57. Okay, and D3 is 0.5 plus 0.04, sorry, 0.06. It is 6 times of 0.01 plus 0.03. So it is equal to 0.59, right? 0.59 centimeters. So you got three readings. And now you just need to take the average of them. Okay, the mean of them. So D is equal to D1 plus D2 plus D3 divided by 3. So tell me what's the average? 0.61 plus 0.57 plus 0.59 divided by 3. Tell me. What's the answer? Is it 0.59, right? Then next, let's talk about another measuring instrument. So that is screw gauge or screw gauge. Okay, however you pronounce it, right? So screw gauge. So now this is used to take finer measurements. For example, you want to measure width of a cable, width of a wire, okay, radius of a wire. So for that purpose, you will make use of screw gauge, right? So now it looks like this, and suppose you want to measure the width of a wire. So you will put the wire like this here, okay, and then you will tighten up the screw, right, using this part which is known as ratchet, okay, and then this body of the screw gauge, this is known as thimble, right? and you can see there are markings here. So this one is the main scale of the screw gauge, this one is the main scale, and this one is the circular scale. So as you give rotations to the ratchet, the circular scale will rotate, okay, and you will get some reading, right? So now when there is nothing kept in between the, you can say the gap of the screw gauge, right? So nothing kept here, then the screw is perfectly tightened. In that case, what should happen? Actually, this horizontal line on the main scale, it should match with the 0 of the circular scale. Okay, it should match with 0 of the circular scale. So in that case, there won't be any 0 error. Okay, but there can be some 0 error, so we'll talk about that. So now when you give one rotation to this ratchet, then screw moves ahead by some distance, and that distance is known as the pitch. Okay, that distance is known as what? The pitch. Okay, when you rotate the ratchet by 360 degrees, the screw moves ahead by some distance. That distance is known as pitch. And what's the pitch? So you can see that it will exactly move ahead by the distance equal to the distance between two threads of the screw. Okay, it will move the exact distance by which it moves, it's equal to what? The distance between two threads of the screw, right? So what is pitch? Pitch is the distance between two threads of the screw, and when you give one rotation to this ratchet, then the screw gauge, it will move through the distance of, or the screw will move through the distance equal to what? Pitch, right? This thing is clear. So how do we find the least count? See, when you rotate this screw gauge or the screw by 360 degrees, it will move through the distance equal to what? Distance equal to pitch. Okay, and on the circular scale, you divide it in n parts, suppose. Then the least count would be equal to pitch divided by number of divisions on circular scale. Okay, so the least count is what? LC is the pitch divided by number of divisions on the circular scale. So for an example, pitch is 1 mm and number of divisions on the circular scale is 100, then the least count would be equal to 1 by 100. Okay, 1 by 100 mm. So this is very simple, right? So then let's talk about the 0 error. Okay, so here, see, in this case, there is no 0 error. You are measuring nothing, then the screw would be perfectly tightened. So the main scale, the horizontal line on the main scale, it matches with the 0 of the circular scale. So in this case, there is no 0 error, right? So here you can see this is positive 0 error. Okay, how is it positive? The horizontal line on the main scale matches with 1, 2, second line. Okay, second line of the circular scale, then this is positive 0 error. So this is equal to 2 times of the circular, the 0 error is equal to what? 2 circular scale reading multiplied by whatever is the least count, right? And this one is the negative 0 error. So in this case, you can see, okay, so 0 is over here, and you have 1, 2, 3, 4. Okay, fourth line is matching, okay, with the 0, right? So then this is the negative 0 error. Okay, is this thing clear? Tell me. Right? Okay, good. So this is minus 4 CSR. Okay, this much is the 0 error. So then let us see some problems based upon the screw gauge. So a screw gauge has least count of 0.01 mm and there are 50 divisions in its circular scale. The pitch of the screw gauge is, so this is very, very simple. So here we want to find out pitch. So you have formula that least count is equal to pitch divided by number of divisions on the circular scale, and therefore what is pitch? So pitch is equal to least count multiplied by number of divisions on the circular scale. right? So least count is given and number of divisions on circular scale is given. So it's 0.01 multiplied by 50 and this thing is in mm. So multiply this, so you get 0.5, right? 0.5. So 0.5 mm and that's the answer. Okay, this one is from NEET 2020. Very simple question, right? Okay, good. And let's see next one. If the screw on screw gauge is given 6 rotations, okay, so number of rotations is 6. It moves by 3 mm on the main scale. It moves by 3 mm on the main scale. If there are 50 divisions on circular scale, the least count of the screw gauge is. So this is also very simple. So first of all, find out the pitch, right? How will you find out pitch? So pitch is distance covered in one rotation, right? It's the distance covered in one rotation. Distance covered per rotation, you can say. So it is distance covered divided by number of rotations. Okay, distance covered divided by number of rotations. So that is 3 mm. Okay, they have given that when the screw gauge is given 6 rotations, the distance covered is 3 mm. So it's 3 divided by 6 rotations, right? So you will get distance covered per rotation. Okay, so 3 divided by 6 means 0.5 mm, because this was 3 mm, right? So 0.5 mm is the pitch. Okay, then how do we find the least count? The least count is just pitch divided by number of divisions on the circular scale. So that is pitch is 0.5 mm and number of divisions on the circular scale is 50. So you have 0.5 divided by 50 or 5 divided by 500, and if you divide that you will get 1 by 100, that means 0.01. Okay, 0.01 mm. Is there such an option? Yeah, it is there. It's given in centimeters, right? 0.001 mm means 0.001 centimeter, because 1 mm is 0.1 centimeter. So if you multiply that, you will get this answer. So it is equal to 0.001 centimeters, right? So that's the answer. This one is clear. Okay, good. Let's see next one. Using screw gauge of pitch 0.1 centimeter and 50 divisions on its circular scale, the thickness of an object is measured. It should correctly be recorded as. Okay, right. So now you have some object and you are measuring its thickness using the screw gauge. So pitch is 0.1 centimeter and there are 50 divisions on the circular scale. So there are these options. So first of all, what you should do in such a question is find out the least count. Okay, so find out least count. So it is pitch divided by number of divisions on the circular scale. So that is 0.1 centimeters, right? Centimeters divided by n is 50. So 0.1 divided by 50 means 1 divided by 500, right? 1 by 500 means it is 1 by 5 into 10 raised to 2. Take that to numerator. So you get 10 raised to minus 2. Okay. So and 1 by 5 will give you what? 0.2. 0.2 multiplied by 10 raised to minus 2. So 0.2 multiplied by 10 raised to minus 2 of a centimeter. Right, that means 0.002 centimeters. Okay, so that is 0.002 centimeters. Then using this one, which of the readings, out of these, which of the reading can be taken? Tell me. Okay, if you look at the options, see, this is simple. If you look at the options, 3 of the options are, they have this last digit, okay, it is odd in them, right? It's odd, odd, odd. And in this one only, the last digit is even, right? And when you will take the reading using a device which has this kind of least count, this kind of means the last digit is even, then the reading will have the last digit of the reading would be even, right? Because see, the minimum reading that you can take is 0.002, okay, then next reading that you can take would be equal to what? So first one is 0.002 centimeters. This is the least that you can measure. Next reading that you can take is 0.004 centimeters, okay, twice of this, right? Next is thrice of this, so that would be 0.006 centimeters, right? Next can be anything, let's say 31 times of this. So if you take 31 times of this, that would be 0.062 centimeters, right? Then you can take 500 times of this. Whatever reading that you take, okay, it will be in multiples of this least count, and therefore the last digit cannot be odd. The last digit has to be even, and that's why this would be the answer, option B, right? Okay, good. All right, so this is good question. Let's see next one. A student measured the length of a rod and wrote it as 3.50 centimeters. Which instrument did he use to measure it? Okay, then see, look at the reading and identify the least count. What can be the least count of this? It can be either 0.01, right, of centimeter, or it can be 0.02 of centimeter, because this is even, okay? So a meter scale, can you measure this using a meter scale? No, right? Because on meter scale, what would be the least count? Least count would be equal to 1 mm, right? The least count would be equal to 1 mm, that is 0.1 of centimeter, and this is beyond that, so you can't use meter scale. Vernier caliper where 10 divisions in vernier scale match with 9 divisions in main scale, and main scale has 10 divisions in 1 centimeter. That means for this one, for option B, you have MSD is equal to what? Main scale division is equal to 1 divided by 10 of centimeter, right? Because it has 10 divisions in 1 centimeter, right? So therefore, what is main scale division? It's 1 by 10 of centimeter. And then they say that 10 divisions in the vernier scale match with 9 divisions on main scale. So what is, so from that you can find out least count, right? So in such a case, least count is just equal to what? 1 by number of divisions on the vernier scale multiplied by MSD. So that's 1 by 10, right? Times of main scale division is also 1 by 10. So that's 1 by 100, means 0.01 of a centimeter. So can it be used to take this kind of a reading? Okay, you found the least count already. It's 0.01 or 0.02. Look at the last digit. Okay, the decimal point where the last digit, the number of digits after the decimal point. Okay, so then it's 0.0. See the last digit, it is even, so either it can be 0.01 or 0.02, right? If it was odd, then it could be just 0.01, right? This thing is clear, tell me. Yes, no? Okay, so that's why this is the answer. Now you don't need to check the other options, but we'll check. A screw gauge having 100 divisions in the circular scale and pitch of 1 mm. Okay, so least count of option C is 1 by 100, right? Because pitch is 1 and there are 100 divisions in the circular scale. 1 by 100 of 1 mm. So that is 0.001 of a centimeter, right? And a screw gauge having 50 divisions in circular scale and pitch as 1 mm. So again 1 divided by 50 of mm, that is equal to 0.02 of mm, that means 0.002 of centimeter, right? Okay, so are the last two clear? Tell me. Least count of last two. Okay. Okay, so you have problem in this one. All right, I will explain once more. So you have Vernier caliper where 10 divisions in vernier scale match with 9 divisions in the main scale, right? And in such a case, whenever you have n divisions of vernier scale matching with n-1 divisions on the main scale, then in that case the least count is what? 1 divided by number of divisions on the vernier scale multiplied by MSD. Okay, what is MSD? Mahendra Singh Dhoni. Okay, what is MSD? It is the main scale division, right? So find out the main scale division using this one. So they say that main scale has 10 divisions in 1 centimeter. So suppose this is this much distance in 1 centimeter and it has got 10 divisions. That means what is the main scale division? It's 1/10 of that, right? This is 1 centimeter and it has got 10 divisions. So what is this much division? It's 1/10 of that, right? Is this thing clear? So main scale division is 1/10 of a centimeter. Okay, and the least count is 1 by n times of this thing. So 1 by n, and they say that number of divisions of the Vernier caliper is 10 that match with 9 divisions on the main scale. So in that case it's 1 by 10 of MSD, and MSD you calculate it is 1 by 10 of centimeter, 1/10 of a centimeter. So 1 by 10 times 1 by 10 of a centimeter, that means 0.01 centimeter, right? Is this thing clear? Okay, good. And this reading, if you look at this reading, either it's taken using a device having least count of 0.01 centimeter or 0.02 centimeter, right? Because this is even number. Okay, if it was odd number, then you can say it's 0.01 centimeter only. Any one, either of the two, right? But we have one device. This device has least count of 0.01 centimeter. So this reading can be taken using this device. That's why that's the answer. Okay. Understood, right? Okay, good. Let's see next one. A student measured the diameter of a small steel ball using screw gauge of least count of 0.001 centimeter. The main scale reading is 5 mm and 0 of circular scale division coincides with 25 divisions above the reference level. Okay. Then if the screw gauge has 0 error of minus 0.004 centimeter, the correct diameter of the ball is. This is also simple. See, it is main scale reading plus circular scale reading, right? Main scale reading multiplied by MSD, okay, plus circular scale reading multiplied by the least count plus the 0 error. That's your reading, right? So reading is a diameter of some ball. Okay, so this is the formula, right? So then what is the main scale reading? So they have directly given the complete reading of the main scale. Okay, it's 5 millimeters, right? They have not given number of divisions, right? Number of divisions, they have directly given the answer. So it's 5 mm plus what is circular scale reading? It is 25 divisions, right? It's 25 divisions multiplied by what is the least count? 0.001 centimeter, but this one is in millimeters, this one is in centimeters. So let's write the units, and then zero error is negative, so you need to add up that much of value. So that is 0.004 of a centimeter, right? So just convert this thing in centimeters, nothing. So 0.5, this is 0.5, okay, because all of the options are in centimeters. 0.5 plus 0.025 plus 0.004, add it up. 0.025 plus 0.004 will give you 0.029, right? And add it up in this one, so it will give you 0.529, okay, centimeters. That's the answer, 0.529. It's option D, right? This is clear. Okay, so most probably there can be a question out of these two measuring instruments, the vernier caliper and screw gauge. So this was important, this is important, okay, and this was there in earlier syllabus too. Then let's move on to next experiments. So one is the dissipation of energy of a simple pendulum, okay. So now, what is energy of the simple pendulum? So we know energy of a simple pendulum, if there is no dissipation, it's half of Ka square, right? So that is equal to half of m omega square. Okay, so you know the energy of a simple pendulum is given by this formula, half of Ka square, and that is equal to half of m omega square a square. This is considering that the amplitude of oscillations will remain constant, right? For an example, suppose you have a pendulum like this one, okay, so this is a pendulum, right? And this is charging cable of my watch, okay, so that's not important. So any mass suspended from a cable will give you a pendulum, right? Okay, so then you give it a displacement and release it, then it will oscillate like this, okay, but after some time you can see what happens, the oscillations die out, okay, the oscillations die out, and now it's almost steady, right? So it's not like it will keep on oscillating forever, okay. Why do the oscillations die out? The oscillations die out because of what? The viscous force due to the air, okay, the air will oppose it, okay, that's why the oscillations will die out. So we need to find out the dissipation of energy of a simple pendulum, okay. So what will we do? We can just plot a graph between this a square, amplitude square, versus time, okay. So we start with this kind of a setup, right? So this is just a stand, here there is a split cock, and then there is a wire. So now you don't need to remember all of these details, right? There is some pendulum, there is this wire, and a mass is connected to that, okay, right? And then that mass oscillates. Then what will you do? You will just plot a graph between amplitude square versus the time, okay, and you will see that the graph between amplitude square, a square versus time, it will fall like this, okay, because see here a scale would be marked, right? A scale would be marked here on the table, right? On the table it will oscillate, and then you start a stopwatch. So at the beginning there would be some amplitude, right? What is amplitude? The extreme distance up to which it goes. Then that amplitude will go on decreasing. So in first oscillation you will note down the time, and you will note down what? The amplitude. In next oscillation again you will note down the time, you will note down the amplitude. Then in next oscillation again you will note down the time, you will note down the amplitude, right? And you will get several points. Then you will take square of amplitude and you will plot it against the time, okay. So you will get several points, like this, something like this, and then you join those points and you plot this graph. Okay, so that's very simple, and you will see that it follows this kind of a behavior. Okay, so this one is known as an exponential curve, or this is known as exponential decay actually. Okay, so it's known as an exponential decay. So if you join these points, you will see this kind of a curve, right? Generally, if you plot displacement versus time graph of a simple pendulum, if there is no dissipation of energy, no loss of energy, the graph will go like this. Okay, amplitude will be constant, right? Now, as we have seen, the displacement will die out. Okay, displacement will die out, right? So in this case, now what happens if you plot the graph of displacement versus time, x versus t, the graph will go like this. Okay, so now if you take envelope of this graph, okay, so this is envelope of the graph, right? This dotted line is envelope of the graph. It shows exponential decay pattern. Shows what? Exponential decay pattern. And now this formula, it will not be asked because damped oscillations is removed from the syllabus. Okay, the formula for displacement is x equal to a naught e raised to minus bt by 2m times of cos of omega prime t minus phi. So the frequency of oscillation, omega, which used to be square root of k by m, it also changes. It is different in case of damped oscillation, right? And the amplitude is not constant. Okay, so key takeaway here is amplitude is not constant. So this term can be written as an amplitude. So what is amplitude? E raised to minus bt by 2m. Okay, e raised to minus bt by 2m. That means amplitude decays exponentially. And if you put this amplitude in this formula, okay, energy is half of k square, then what do you get? Energy also decays exponentially because at square would be what? It is a naught multiplied by, actually it's a naught multiplied by this thing, right? It is a naught, its original amplitude multiplied by this factor. Okay, so then if you put it in this formula, then what will you get? Half of k multiplied by a naught square times this term square. That means e raised to minus b by m, right? It's e raised to minus b by 2m times t. Square of that would be e raised to minus b by m times t. Okay, so the key point is it falls exponentially, right? It falls exponentially. The energy or the amplitude falls exponentially. Is this thing clear? Tell me. Right? So then let's see some problems based upon this. Which of the following represent correct graph for the amplitude with time of damped SHM? Tell me. Option 1, 2, 3, 4. Which one? Option 3, right? Then which of the following represent the graph of energy with time of for a damped SHM? Again, 1, 2, 3, 4. Which one? It's 2, right? It's very simple. Okay. The next one, the amplitude of damped SHM, okay, amplitude of damped SHM becomes half in 1 minute and 1 by x times in 3 minutes. Then the value of x will be, tell me. It becomes half in 1 minute, okay, and 1 by x times in 3 minutes. So tell me what will happen. All right, this is very simple. See, let's say amplitude is a, okay. After 1 minute, what happens? It becomes a by 2. Okay, so this is very simple trick. Then now amplitude is A by 2. After another 1 minute, what will happen? It will become half of that, right? So half of A by 2 means A by 4. Okay. Then after another minute, okay, it's A by 4 now. After another minute, what will happen? It becomes 1 by 8. Okay, half of A by 4, that means 1/8. Okay, so therefore after 3 minutes, what happens to the amplitude? It becomes 1 by 8. Okay, so what is x? It is 8. Right, this thing is clear. See next one. In damped oscillation, the amplitude after 50 oscillations is 0.8 A0, where A0 is initial amplitude. Then amplitude after 150 oscillations is, so the amplitude after 50 oscillations is 0.8 A0, right? So it was A0, and after 50 oscillations, what happens? It becomes 0.8 of A0, right? After 100 oscillations, what will happen? It will become 0.8 of 0.8 A0. It will become 0.8 of this oscillation, this amplitude, right? After another 50 oscillations, that means whatever is asked, right? 150 oscillations, that means after another 50 oscillations, okay, it will become 0.8 of 0.8 of 0.8, that means 0.8 cube of A0, and that's the answer. So what is 0.8 cube? 0.8 square is 0.64. 0.8 of 0.64 would be, I guess it would be this option 2, right? Is this one clear? Okay, so this kind of questions can be asked based upon this experiment. Very simple experiment, right? Let's see next one. This one is even simpler than the earlier. Okay, so to determine the mass of a given body using meter scale by principle of moments. Okay, by principle of moments. So we have solved this in rotations. Okay, in rotational equilibrium. So see, this is a meter scale and it is pivoted at this point, exactly at the middle, right? So now there are these two hangers, you can say, and those are weightless, suppose weightless hangers, and then you put some weights, okay, in those hangers, right? So then now what will happen? Because of this weight will try to rotate the meter scale this way. This one will try to rotate the meter scale in this way. Okay, it's like your seesaw, right? So then at some point it can be balanced by putting certain ratio of weights, right? And how can we find that? So we know that it will be, this meter scale will be in rotational equilibrium when the total torque acting on it is equal to 0, right? So you know that for rotational equilibrium, the next, the total torque, the net torque, we can say it's equal to 0, right? So torque due to this, suppose positive, because it wants to rotate this meter scale in anti-clockwise sense. So suppose anti-clockwise rotation is positive and clockwise rotation is negative, right? So then it is at distance, this force is acting at a perpendicular distance of r1, this one is acting at perpendicular distance of r2, right? So you can say r1 times of the force is F1, first force is F1, this force is F2. So what is torque? R1 times of F1, okay, and minus R2 times of F2 is equal to 0, right? Then only it will be balanced. So that is R1 times of m1g, that is the force, minus r2 times of, or you can take that r2 times F2 on other side, it's r2 times of m2g, and g gets cancelled. So then suppose this one is known, right? This mass is known, the other one is unknown. Okay, m1 is known, m2 is unknown, right? So m2 is unknown. Just for an example, it can be m1 unknown, m2 unknown, right? Any one of them. So this one is unknown. And then what would be m2? Just move that r2 on other side. So it is equal to r1 by r2 times of m1. And that's the experiment, right? Is this thing clear? Tell me. So there would be some unknown mass on one side, okay, but distance would be known, r2 would be known, and you put some weights on the other side. Those weights would be known, right? And you just find the distance, or suppose you are given with some weights and you just move this, okay, shift this weight to such a location where it will be balanced. Okay, either the distance will be fixed and weights will be changed. Okay, weights could be changed, or the weight is fixed and you could change the distance, right? Out of the two, right? Any one is the case, suppose. So this is the relation between m2 and m1. Okay, m2 would be equal to r1 by r2 times of m1. This is the formula. Very, very simple experiment, right? Very simple experiment. Okay, so let us see a problem based on this. In an experiment with meter scale, an unknown mass m is balanced by two known masses of 16 kg and 4 kg as shown in the figure. Okay, so in first one, this mass m is unknown, it's balanced by 16 kg, right? And then in the second case, it is balanced by 4 kg. But in first case, the distances are, this is L1, this one is L2, and in second case, this is L1 and this is L2 again. Again, the distances are same, but now that masses, you can see, in first case, it's on the right hand side, in the second case, it is on the left hand side, right? So from first case, case 1, what would be m? So from case 1, you have m equals to L1 by L2 times of 16, right? M is equal to L1 by L2 times of 16. Okay, and in second case, what is m? So in second case, it's L2 by L1. It's L2 by L1, right? L2 by L1 times of 4. Okay, so how can we find m then? Either what you can do is, you can substitute L1 by L2 from this equation, in this equation, right? Or what you can do is, you can just multiply out these two equations. So if you multiply 1 and 2, this is case 2, and right, if you multiply 1 and 2, 1 times 2 will give you what? On left hand side you will get m square, and on right hand side it's L1 by L2 times of L2 by L1, so that gets cancelled out, and then you have 16 times 4 is 64, right? So this thing will get cancelled out. Okay, L2 L2, L1 L1 get cancelled out, and m square is 64, means m is equal to 8. M is equal to 8 kgs. So this is again a simple question, right? Tell me. Okay, good. Very simple. See next one. A uniform meter scale is kept in equilibrium. It is supported at 60 centimeter mark, and the mass m is suspended at 90 centimeter mark. Okay, so meter scale is suspended, it is in equilibrium, it's supported at 60 centimeter mark, and mass m is suspended at 90 centimeter mark as shown in the figure. What is the relation between weight of the scale and weight of the mass? Right. So now weight of the scale, where will it act? Okay. At which point can we consider the weight of the scale is concentrated? The weight of the scale would be considered to be concentrated at its center of mass, right? That's equal to 50 centimeters. Weight of the scale is equal to what? Sorry, weight of the scale acts at the midpoint, right? So now this is a weird scale. Seems like this should be the midpoint, right? Anyways, but they have marked it 60 centimeters, no problem. So weight of the scale will be acting downwards from this point, the midpoint, right? Then it's very simple. The weight is W. So for the scale to be in equilibrium, the net torque must be equal to 0. So net torque is equal to 0, and therefore you have R1 times W. Okay, this much distance is suppose R1 times W minus R2 times M is equal to 0, right? Because this will rotate the scale in anti-clockwise and the other mass will rotate the scale in clockwise. So anti-clockwise rotation will consider positive, clockwise negative, right? So then we just want to find out the relation between them. Okay, so put the values. R1 is what? It's 10 centimeters. It's 10. So 10 times of W is equal to what's R2? And this is 90 minus 60, right? This much distance is 30. So 10 times of W is 30 times of M, and therefore W is equal to 30 by 10 means 3 times of M. So W is, so they have not given the values. They are asking whether it's greater, less, or it's equal to M. So it's definitely greater than M. Okay, it's greater than M, right? This one is clear. Tell me. Okay, good. Then let us see next experiment, right? Because this one was very simple. So let us see next experiment, that is Searle's experiment to determine Young's modulus. Okay, so how is this experiment? Can you see this diagram, or is it very faint? Tell me. Here what do we have? Here we have two wires, right? And then there are these two frames, and they are connected by means of a rod, let's say, and there is this horizontal tube which contains some spirit. Okay, and there is a bubble. So this tube is transparent, okay, maybe made up of glass, and there is a small bubble, okay, in the spirit. So now see, when two frames they are at the same level, then what will happen? The bubble will be exactly at the middle. Okay, the bubble will be exactly at the middle. When one of the frames moves down, then what will happen? The bubble will also move, right? It will either shift towards left or it will shift towards right. Suppose this frame moves down. Okay, this frame moves down. How will it move down? If one of the wires gets extended, right, then the frame will move down. Okay, so in that case what will happen? The bubble will shift towards left. Okay, it will move higher, right? So what you can do in this experiment is, see, there would be these two wires have these two frames connected to them, and there are these two hangers where you can hang the weights. Okay, so at the beginning there will be equal weight in the left pan and right pan, okay, which are connected to the hangers to just straighten the wires, nothing else, right? And in that case the bubble will be at the middle. And then what you do is you just put weights in one of the wires. Let's say this is the experimental wire, okay, and this is the test wire, okay, this one is called as test wire. So then in reference with this wire, you can call it actually one is the experimental or test wire, okay, and the other one is reference wire, right? So one is the reference wire and one is the wire under observation, right? That is the experimental wire. Okay, so you put the weights there, then what will happen, that experimental wire will move down. Okay, the wire whose Young's modulus you want to find out, it will move down. Move down means it will extend, right? This thing is clear. When you put some weights, what will happen to this wire? Its length will increase. So what you do, you put the weights and there is this arrangement, there is a screw gauge here, okay, and what you do is actually you rotate the screw, okay, there is a micrometer here, you rotate the screw of this micrometer and you take a reading. I mean, what you do is you again balance this bubble in the spirit, okay, so it will shift on one side, then you will rotate the screw in such a way that this thing is balanced, okay, then you will take the reading, okay, in that way you measure the change in length, right? Okay, how much the screw you need to rotate, okay, you will take that reading and then you will get the measurement of length from there, right? So for this much amount of weight, this much is the change in length, okay, so then you will find out the strain, that is delta L by L, right? You will find out the stress. So what is stress? This is strain is delta L by L. What is stress? So stress is force per unit area, right? So that means you know original length of the wire, you also know the area of cross section of wire, so you measure that beforehand, okay, you measure that beforehand using a micrometer screw gauge, you measure the area of cross section, right? And then you know Young's modulus is just stress divided by strain, right? Young's modulus is just stress divided by strain, that is F upon A divided by delta L, and the L will come in the numerator, right? That is FL divided by area of cross section of wire would be pi r square, okay, pi r square times delta L. So this is the formula, okay, so you will plot a graph between stress and strain, you will plot a graph between stress and strain, and then what is the Young's modulus? It's stress divided by strain, so you will just take slope of that graph, right? So we have studied this thing actually, and then you will measure the Young's modulus. So is the experiment clear? Tell me yes, no. Is there any doubt? No doubt, right? Very simple experiment. Okay, so we have already solved many questions based on this, but anyways, let us solve some questions. In Searle's experiment, following 4 wires are made of same material. Which of these will have largest extension when the tension is applied? So this kind of question also we had solved earlier. Okay, so we want change in length, largest change in length. Okay, so what is given? Diameter is given, length is given. Okay, so then use this formula. Using this one, I can say delta L is equal to force times L divided by, I will move y on this side, so it is pi r square times y, pi r square times y. So you can say it's directly proportional to L, so delta L is directly proportional to L divided by what? R square. Because here diameter is given instead of radius, you can say it's inversely proportional to diameter square, right? Because it's inversely proportional to R square and diameter is just 2 times of R. Okay, using this, just find out in which of the case this L by D square factor is largest, and in that case only the largest extension will happen, right? So this is very simple. Yes, no? So let's find it out. So in first case, L by D square is what? 300 divided by 3 square. Okay, in second case, all right, so this is 300 divided by 3 square means 100 divided by 100 by 3. 100 by 3. In second case, it's 50 divided by 0.5 square. Right, so let's do one thing. Yeah, tell me.
Sir, it will be 100 divided by 9.
No, 300 divided by 9. Right, diameter square is 9. Okay, so then I have divided numerator and denominator by 3. So this is 100 divided by 3. Right? So then here what I can do is I can multiply numerator by 2. Okay, and denominator, actually we'll need to solve this, right? So multiply this thing by 2. Okay, so we can make the numerator same. Then if the denominator is more, that means the extension would be less, right? That means fraction would be less, right? So this is 100 divided by 0.5. This one will give you 100 divided by 0.5, right? I'm multiplying numerator and denominator both by 2, right? So it's 50 by 2, 50 times 2 is 100, 0.5. This is 0.5 times 0.5. 1 of the 0.5 times 2 is 1. Then what remains is 0.5. Okay. In third case, it's 100 divided by 1 square. So that is 100 divided by 1. And in fourth case, it is 200 divided by 2 square. So it's 200 divided by 2 square means 4. So 100 divided by 2. So in which of the case this fraction is largest? If denominator is more, that means fraction would be small, right? If denominator is less, fraction would be more. So I guess in second case, it is 100 divided by 0.5. This one would be largest, right? This one would be largest. So extension will also be largest in the second case. This thing is clear, right? It's simple. Okay, good. Let's see next one. This is copper of fixed volume V is drawn into a wire of length L. When the wire is subjected to a constant force F, the extension produced in wire is delta L. Which of the following graphs is a straight line? Okay. Which of the following graphs is a straight line? Delta L versus 1 by L, then delta L versus L square. So actually, if you make use of the formula says that it is F, you want extension versus something, right? So extension can be written as FL divided by, I will say pi r square is AY. Okay. So extension delta L is equal to FL divided by AY, right? And then A and Y are constants. Okay. So why I'm saying area is not constant, because if you increase the length, then what will happen to the area? Area will decrease. But then they have said that it's the fixed volume. Okay. The wire has fixed volume. Okay. That means volume is constant. Volume is constant means, if volume is constant means area times length is constant. Right, area times length is constant. Okay, and therefore what you can say is area is equal to some constant, let's write it as K, divided by L. Okay, you can write area is equal to some constant. What is that constant? Actually it's volume only, right? But let's write it as area is equal to a constant divided by L, right? You can substitute that here, and then what do we get? It is F upon Y, and area can be written as a constant divided by L, and there is one L in the numerator. Move this L in the numerator, so you get this is some constant, right? Force Y and K. Okay, this is some constant because it is pulled by a constant force. Young's modulus will be a constant, right? So then you get delta L is directly proportional to L square. That means the graph of delta L versus L square would be a straight line. Okay, this thing is clear? Tell me. The graph of delta L versus L square would be a straight line, right? So this is very simple. Okay, good. Then let's see next one. Now this one is not directly related to that experiment, but we are making use of that formula. Okay, that's it. All right, let's see next one. In determination of Young's modulus of elasticity of wire, a force is applied and extension is recorded. Initial length of wire is 1 meter. The curve between extension and stress is depicted. Then the Young's modulus of wire will be, so extension and stress, this curve is given. Extension versus stress is given. Okay, and what is the length of wire? Length is equal to 1 meter. What they have given is extension, means delta L versus stress. Okay, this curve is given, right? Now if length is equal to 1 meter, then even if we divide by length, the curve will remain same, right? Because L is just equal to 1, so this curve will remain same. Okay, so that means what we can say is on horizontal axis there is a stress, and on vertical axis there is strain, right? So then what is Young's modulus? It is stress by strain. So it is slope of stress strain curve, but then it is slope of what? There should be stress on vertical axis and strain on horizontal axis if you take slope of that curve, right? So here what we'll do is we'll take reverse of slope of this one, right? That means what is stress? Change on the vertical axis divided by change on horizontal axis. Here stress is on horizontal axis, so we'll take the change on horizontal axis divided by the change on vertical axis, right? So that is 8,000 minus 4,000. Okay. You have 8,000 minus 4,000, this point and this point, divided by 4 minus 2. Okay, and then we need to change the unit also, that's in millimeters, so we'll need to change it to meters. So it is 8,000, right? Can you see that? 8,000 minus 4,000 divided by 4 minus 2 times 10 raised to minus 3, right? This is clear. 8,000 minus 4,000, this is in proper units. Okay, no, this is also in kilonewtons per meter square, so you need to convert that to newtons per meter square. Okay, so this thing also will multiply by 10 raised to 3 to convert to newton per meter square, right? And on vertical axis this is 2 mm, we need to convert it to proper units, so it will be 2 multiplied by 10 raised to minus 3, right, meters. Okay, so numerator also we need to multiply by 10 raised to 3 multiplied by 10 raised to 3. Right, this thing multiplied by 10 raised to 3, then that is 4,000 divided by 2, that's 2,000, and 2,000 times you have 10 raised to 3, then this thing is again 10 raised to 3, so it will be 10 raised to 9. 2 times 10 raised to 9, right? 2000 multiplied by 10 raised to 6, that is 2 times 10 raised to 9 Newton per meter square. That's the answer. So again, a very, very simple question, right? Yes, no? Okay, very simple. Okay, let's see next one. In a Searle's experiment for determination of Young's modulus, when a load of 50 kg is added to 3 meter long wire, a micrometer screw having pitch 1 mm needs to be given a quarter turn in order to restore the horizontal position of spirit level. In a Searle's experiment for determination of Young's modulus, when a load of 50 kg is added to a 3 meter long wire, micrometer screw having pitch 1 mm needs to be given a quarter turn in order to restore the horizontal position. Okay, so now load of 50 kg is added, length of wire is given, so F is equal to mass of the load is given, right? F is equal to mg, which is 50 times acceleration due to gravity, right? Whatever it is, let's take 10, no? 50 times 10, 500 newtons. Okay, length of wire is given, right? It's it's 3 meters, and then okay, a micrometer screw having pitch of 1 mm needs to be given a quarter turn. This is given. Another condition given in the problem is a micrometer screw having pitch of 1 mm needs to be given a quarter turn in order to restore the horizontal spirit level. So that means what is the change in length? It's equal to quarter turn, right? 1/4 of quarter turn means 1/4 of the pitch. Okay, what is the pitch? So screw has pitch of 1 mm, right? So delta L would be equal to 1/4 of that pitch. Okay, 1 mm. If 2 rotations were given, then delta L would be equal to what? 2 times of the pitch. 1/4 rotation is given to restore the wire back, right? Restore the spirit level back. That means the delta L is equal to what? 1/4 of the pitch. This thing is clear? Tell me. 0.25 mm. Okay, yes, no? Right, good. Then the Young's modulus of wire if its cross-sectional area is 10 raised to minus 5 meter square. So this is simple. Cross-sectional area is given 10 raised to minus 5. Okay, that's in meter square. So then Young's modulus is just force by area divided by delta L by capital L. That will go to the numerator. This is the formula. So put the values. Force is 500 newtons. This is 10 raised to minus 5. Delta L is 0.25, but it's in mm, so that's 10 raised to minus 3 in meters. Then wire has length of 3 meters. Okay, so just take that 10 raised to minus 5 and minus 3 in the numerator. So it is 10 raised to plus 8, right? So then you have 1500 times 10 raised to 8 divided by 0.25. So 0.25 can be written as what? 1 by 4. Again, take that 4 to the numerator. So that's 1500 times 4 is 6000. 6000 times it was 10 raised to 8, right? 6000 times 10 raised to 8. So what's that? 6 multiplied by 10 raised to 11 Newton per meter square. So that is 5.88 into 10 raised to 11, 1.5 into 10 raised to 11, none. So actually answer is 5.88. And why did our answer came out to be equal to 6 times 10 raised to 11? It's because of we took G as 10, right? If you take it 9.8, so I guess this would be the answer. This one is clear? All right. So next one is capillarity. So what is capillarity? It's the phenomenon or rise or fall of a liquid in the capillary tube, right? Capillarity is the phenomenon of rise or fall of a liquid in a capillary tube. So now we are going to make use of capillarity to find out surface tension of the liquid. Okay, so the rise or fall of the liquid in capillary tube is given by this formula: H is equal to 2t cos of theta, okay, divided by r rho g, where r is radius of the capillary tube. Okay, so now what is theta? So theta is angle of contact. Theta is what? Angle of contact. So if you remember, so now this liquid which is in contact with the solid makes some angle. Okay, so that angle is known as angle of contact. So angle, that free surface of liquid. So if you see this capillary tube, then it will make some this kind of meniscus, right? It will make this kind of a meniscus. So then this is the free surface of the liquid and this is the solid surface. The angle between them is known as angle of contact, right? So the height of the liquid column in the capillary tube is given by this formula: 2t cos of theta divided by r rho g. Now these terms are self-explanatory. What is T? T is the surface tension, R is the radius of the capillary tube, then rho is the density of this liquid, and G is acceleration due to gravity. So you already know this formula, right? And then now we want to measure the surface tension using this capillary rise method. So this is the experimental setup. What you do is you take this beaker, you fill it with water or some other liquid whose surface tension you want to measure. Then there is the stand. So the stand, it will hold the capillary tube and the spin. Okay, so what does the spin do? So now you will adjust the location of the spin in such a way that tip of the pin just touches the water level. Okay, it doesn't enter the water or whatever liquid there is, right? It will not enter the liquid, and the tip will not be, there won't be any distance between the surface of the liquid and tip of the spin, right? So you have a traveling microscope. When you look through the traveling microscope, you will see a marking like this. Okay, and you want to measure height of this tip, right? That means height of this liquid, okay, or liquid level you want to measure. So you will match this horizontal cross section with the tip, okay, exactly at the bottom of the tip, right? And you will measure the height of the tip, right? That means the liquid level, height of the liquid level, right? Then what you do, then you insert the capillary tube. But before that, what you do is you measure the radius of capillary tube. And how do you do that? So to measure the radius of capillary tube, you take the traveling microscope, okay, and you make it vertical, right? That means you are looking from the top side now, and this is your capillary tube. It will look like this, and these are the markings, okay. This is the marking of the traveling microscope. Then you will mark, you will adjust this marking in such a way that it touches the inner side, because this capillary tube will have very fine bore. It will have very small width, you can say, right? So this is the capillary tube. It will look like this. What you do is you match this inner surface of this capillary tube with the vertical wire like this, okay. You will take one reading, then you will match that vertical wire with the other surface, other inner surface, right? And then using this difference between the two, you can measure the diameter, okay. You can take one reading here, you can take one reading here, and using the difference between two, you can find out the diameter. So to find the diameter, you will need to make that microscope vertical, right? Then once again, now you put the capillary tube into the water, okay. The water or whatever liquid there is, if it is water, the liquid level will rise up in the capillary tube. If it is mercury, then it will fall in the capillary tube, right? Depending upon the wettability of that liquid, if the liquid can wet the solid surface, that means the capillary tube, then it will rise. If it can't wet, then it will fall. That means if angle of contact theta You remember that, right? Angle of contact is small, lesser than 90 degrees, then it will rise up. If angle of contact is less than 90 degrees, then yeah, I said same thing again, right? Angle of contact less than 90 degrees, then it will rise up. Angle of contact more than 90 degrees, then it will fall down, right? Height will fall down. Okay. So now suppose it rises up. Okay. Then you will have this meniscus here. So what you do is, again, you take traveling microscope and you adjust the traveling microscope in such a way that you take it to this level and measure this height. Okay. Right. So you adjust the cross section the horizontal mark in the field of view of the traveling microscope in such a way that it matches with the bottom of the meniscus, right? Either the liquid will form concave meniscus like this, or it will form convex meniscus. If it is convex meniscus, then you will match it at the top. Okay, and you will take another reading. So the difference between this reading and this reading will give you the height. Okay, the difference between that and that reading will give you the height. And you know this formula, h is equal to 2t cos theta divided by r rho g. And using this one, you can just move these things on other side. You can write t is equal to hr rho g divided by 2 cos theta. Right, t is equal to hr rho g divided by 2 cos theta. So you already know the formula. Okay, but now you need to remember this one more formula. So that is, so this is formula with corrected height. Okay, so what is corrected height? So you measured the height, but then see, you measured the height from this lower meniscus, but then there is liquid above this meniscus also, right? If it forms a concave meniscus, then there is liquid above this meniscus also. This thing is clear. So then you adjust for this extra liquid. Okay, so it turns out that the correction is equal to r by 3. So you just write down the same formula that you have marked up, hr rho g divided by 2 cos theta, right? It is the surface tension of the liquid. Then just add, okay, right, keep some space, hr rho g divided by 2 cos theta, and just add r by 3 in h to get the corrected height. Is this thing clear? Tell me. Okay, so this is simple. So this is the experiment. That's it. Okay. Then now let's see some problems based upon this. While performing experiment to measure the surface tension of water using capillary rise method, the necessary precautions to be taken is. Now these precautions are, see, they are like common sense. We'll see that. Okay. Both capillary tube and water should be free from contamination. If there is contamination, what will happen? The surface tension will change, right? If water is contaminated, its surface tension will change. If capillary tube is contaminated, in that case also, what will happen? It will contaminate the water. Okay, so they should be free of contamination, right? There should be no other material. Okay, capillary tube should be clean, while water may contain some dirt or grease. It won't give us the true surface tension, right? So it can't contain, so this is wrong, definitely wrong. Okay, temperature of water should be observed while performing experiment. So the surface tension, as you increase the temperature, we know that the surface tension decreases, right? Surface tension decreases, and that's why surface tension will have different values at different temperatures. So the temperature should be observed while performing the experiment, because at that, see, you are performing the experiment at that time, the temperature would be something. So the surface tension that you get, it is for that temperature. Okay, so this is correct. And internal diameter of capillary should be measured in two mutually perpendicular direction. Okay, so this is also true. See, you measure, let's say this is the capillary tube. So the capillary tube may not be uniform. Okay, maybe the diameter on this side is W, diameter on this side is something else. It's little bit extra or little bit less, right? So what you do is you measure it in two perpendicular directions and then you take mean of those two, okay, and you say that that is the diameter. So this one is also true. So A is true, C is true, D is true. So it's options 3, right? Is this thing clear? Tell me. Yes, no? Okay, good. So this is simple, right? This is simple. Two capillaries of same material but different radii are dipped in liquid. In one of the capillaries, the liquid rises to 22 centimeter and the other 66 centimeter. The ratio of their radii is, okay. Now the formula H is equal to what? 2t cos theta divided by r rho g, right? It's the same liquid, okay. They are dipped in the same liquid. That means surface tension would be constant, rho is constant, g is constant. So what you can say is HR, move that r on other side. So HR would be a constant. Okay, so this is very simple. So now, therefore, H1 or you can say H2R2 is equal to H1R1. Okay, and you want ratio of their radii. Okay, so R1 is to R2 is just equal to R1 is to R2 is just equal to what? H2 is to H1. Okay, so that is H2 is 66, H1 is 22. So 66 is to 22. So that is just 3 is to 1. Okay, so that's the answer. It's option 3. Very simple, right? Tell me, yes, no? Okay, good. Then let's see next one. A liquid does not wet the sides of a solid if its angle of contact is, tell me. Option 2, obtuse angle, correct. Okay, if it is greater than 90, it doesn't wet. We know that. Okay, let's see next one. Water rises in capillary up to a height of 4 centimeter. If it is tilted to 30 degrees from the vertical, then the length of water column in it will be, tell me. So water rises to some height. If it is tilted, if the capillary tube is tilted like this, okay, by 30 degrees. From vertical it is 30 degrees, right? So this angle is 30 degrees. So still the height should be same. Okay, we remember that the height of the water column should be same in both cases. So height should be same. But then what is the length in this tube? So this much is suppose the length and this much is the height. So what's the relation between them? So you can say H by L is equal to what? Cos of theta, right? If you complete this triangle like this, so H by L will give you what? Adjacent side by hypotenuse cos of theta. And you want to find out the length, right? The length of water column now. So it will be equal to H divided by cos of theta. So that is equal to H is 4 centimeters and that is cos of 30 degrees, right? So cos 30 is root 3 by 2. Take the 2 to the numerator. Okay, so it will be 8 by root 3. So 8 by root 3 is the answer. So option A. This one is clear? Tell me. Let's see this one. So terminal velocity. Next experiment. Terminal velocity of a body falling through a viscous fluid. So see, in case of in this experiment, what you do is you drop some object from some height, okay, in a fluid. Now what happens when you drop an object? So initially there would be gravitational force acting on it, because of which its velocity will increase and velocity will keep on increasing. And if there was only gravitational force, then the velocity would have kept increasing, okay, would have just increased, right? But then what happens is there are other forces, okay. So one is the buoyant force due to the liquid, Okay, the buoyant force due to the liquid which acts upwards, and one is the viscous force. Okay, one is the viscous force, right? So viscous force is given by 6 pi eta RV by this is the Newton's formula, right? Sorry, I said Newton's formula. F is equal to 6 pi eta RV. This is the Stokes law. Okay, if the solid body having, suppose this is spherical solid object falling through a liquid having coefficient of viscosity eta and its radius is r, if its velocity is v, then this much would be the force acting upwards. Okay, so now what happens, as its velocity increases, then the viscous force also keeps on increasing, because viscous force, as we saw using the Stokes formula, 6 pi eta RV is directly proportional to velocity. As its velocity increases, viscous force also increases. Okay, therefore now what will happen, at some point the total upward force and total downward force will get balanced, and from that point onwards the body will travel with uniform velocity, and that is known as the terminal velocity. That velocity is known as what? Terminal velocity. Okay, so this is simple, and the terminal velocity is given by this formula. It's 2 by 9 rho minus sigma times r square g divided by eta. Okay, 2 by 9 rho minus sigma r square g divided by eta. And what is rho? So rho is density of the solid object, and what is sigma? Sigma is the density of the fluid. Okay, it can be gas, right? It can be air also, it can be a liquid. Okay, so density of that density of that medium is sigma. And what is eta? Eta is coefficient of viscosity. Okay, or you can just say viscosity. Eta is viscosity, and r is the radius of this ball, or suppose any sphere, right? Solid sphere that you drop through that material, that media. Is this thing clear? This is the experiment. Okay, so now see, this is the experimental setup. Okay, so you have some viscous fluid, viscous liquid, right? You have some viscous liquid. For an example, you have mercury. Okay, very viscous. And then what you do is you drop small lead balls of different radii. Okay, small lead balls are made up of some other metal, you can say. So you drop them, okay, from here, and then you observe the motion of those lead balls, okay, through this glass tube, right? And there are certain markings on this glass tube. Okay, there are certain markings on the glass tube. So what will happen? And you also have a stopwatch. Okay, you also have a stopwatch. You drop it from here. For some time its velocity will increase, and then it will settle down to the terminal velocity. Okay, it will settle down to the terminal velocity. So you observe the time at which it passes through this mark. You press the stopwatch, then the time at which it passes through another mark, again you press the stopwatch. So you measure the time difference between these two markings, right? So using distance divided by time, you can easily find out the velocity. So you find out the velocity, but before that, what you had done is you had found the radius of that lead ball. Okay, so of course using the micrometer screw gauge. Okay, so you found the radius. Okay, you found this velocity. Then what you do is you are taking different lead balls of different velocities, different lead balls of different radii, and then you measure the terminal velocities for all of them. Then you plot a graph between v versus r square. Okay, you plot graph between v versus r square. So take that r square on that side, right? So you plot the graph of v versus r square. Okay, and then see, you know the density of that liquid. Suppose density of the lead ball, okay, g is of course known, and you have found r square by v. Okay, sorry, v by r square or r square by v, it's the same thing. Then there is only one unknown thing, and that is coefficient of viscosity, right? and using this formula then you can find out the coefficient of viscosity. Is this thing clear? Is the experiment clear? Tell me. Okay, good, very good. So then now let's see some questions based upon this. A spherical ball is dropped in a long column of a highly viscous liquid. Okay, spherical ball is dropped. The curve in the graph shown which represents the speed of the ball as a function of time t is. Tell me, speed versus time. Tell me. Simple, right? Initially, when you drop the ball, initially its velocity will go on increasing. Then it will reach terminal velocity when total upward force and total downward force is balanced. It reaches the terminal velocity, and that point onwards, it moves with a constant velocity or constant speed, you can say. So initially the velocity goes on increasing, then at some point it becomes constant, right? So it is graph B. Okay, so that's the answer. Is this one clear? Tell me. Okay, very simple, right? Okay, good. Then let's see next one. Two raindrops reach the earth with different terminal velocities having ratio 9:4. Then the ratio of their volume is. Okay, so see, the terminal velocity is directly proportional to r square, right? Terminal velocity is directly proportional to r square. So using that, what we can do is we can just find out the radius of first one square, right? The terminal velocity Vt is directly proportional to r square. Okay, so we can say r1 square by r2 square is equal to what? V1 by V2, right? Or you can say Vt1 divided by Vt2, right? So the velocities are in the ratio 9:4. That means what's the ratio of radius? R1 by R2 is just square root of that, so that's 3/2. And therefore what is the ratio of volumes? So that's V1 by V2. This is volume, ratio of volumes. Okay, this V is different and this V is different. This is volume. Okay, volume ratio is what? So volume is directly proportional to what? R cube. Okay, volume is 4/3 pi r cube, we know that is 4/3 pi r cube. So V1 would be 4/3 pi r1 cube, V2 is 4/3 pi r2 cube. 4/3 pi, 4/3 pi gets cancelled. So you have r1 by r2 cube. So that's 3/2 cube. So what's that? This is 27 divided by 8. Right, 3 cube is 27, 2 cube is 8. So again a simple question, right? Yes, no? Okay, good, very simple. Let's see next one. A small drop of water falls from rest through a large height h in air. The final velocity is almost independent of h, proportional to root of h, proportional to h, inversely proportional to h. Tell me. A small drop of water falls from rest through large height h. Then the final velocity is. Tell me. Check this graph. It's constant, no? Right? It is almost independent of h. Yes, no? The water drop will fall through some height. Okay, so after some time what happens? The total upward force is the buoyant force due to the air okay, and also the viscous force due to air, right? It will balance the gravitational force, and that point onwards its velocity will become constant. So now that point onwards, suppose it falls to 10 kilometers or it falls through 20 kilometers, does it matter? It doesn't matter. That point onwards its velocity will be constant. So it is independent of h, isn't it? Right? Okay, good. So that's the answer, almost independent of h. Let's see next one. If the terminal velocity of a sphere of gold, okay, sphere of gold having density 19.5 kg per meter cube is 0.8 meters per second in a viscous liquid, and density viscous liquid having density this much, find the terminal velocity of a sphere of silver, okay, of the same size, that means radius is same, okay, and its density is 10.5 kg per meter cube, right? So this is simple. So what we can do is we can make use of the formula. Terminal velocity is equal to what? Terminal velocity is given by 2 by 9 rho minus sigma r square g divided by eta. Okay, so use this formula, 2 by 9 use this formula. So then you have two terminal velocities, one is for silver, one is for gold. So for silver, for gold sphere, for silver sphere, okay, so let's call it Vs, right? So it will be equal to 2 by 9 rho of the silver minus sigma, sigma is the density of the liquid, right, times r square g by eta. So everything else will be a constant. So what I can do is it will be rho for silver minus sigma times everything else. So let's call it constant k, because 2 by 9 r square g and eta are all constants. And in gold, sorry, this is gold, so Vg would be same thing because same liquid, okay, same size, that means eta is same, right? And therefore the constant will be same, so it will be density of gold minus sigma, right? And we are taking ratio of the two, right? So that k will get cancelled. So then just put the values. This is equal to density of silver is 10.5 minus density of the liquid is 1.5 divided by you have 19.5 density of gold minus 1.5. 10.5 minus that is 9 divided by this is 18, that's 1 by 2. So velocity of silver by velocity of gold sphere is 1:2. Therefore velocity of silver is that 1:2 as that of velocity of gold sphere, right? So that was 0.8, so this is 0.4, okay, meters per second. This thing is clear? This one is clear? Tell me. Okay, good. So then this is the kind of questions that will be asked based on these experiments. Okay, so next slot of experiments we'll see tomorrow.